University of Mumbai.
So, let's start. Oh my god, I can hear the door opening. Who's in? Wait, late students? Why are students late to my class? But anyway, I want to ask you one final question. Is this elevator safe to ride? And probably you would answer yes, because it's well below the limit of 2 meters per second and 2.5 meters per squared second. Second squared, actually. So, that is the answer to our Allen machine problem. By the way, can somebody go to the office for me? I have not received my homework booklets yet. I really need someone to go to the office for me. Please? Thank you. Oh! I guess somebody already had the office booklets. So, let's just hand them out. Now you know that coding and physics are so interconnected that they're two faces of the same coin. Now, let's get the homework for tomorrow. Say it louder. Guess I'm gonna come over there so I can hear you guys. Okay. What did you say?
1 upon sine c. 1 upon sine c.
Okay. 1 over sine c? I have no clue what you mean by that, but you're not right. Okay, does anyone have an actual definition of what the critical angle is? And tell me it in words, not equations. Oh, you? Yeah, sorry.
The angle is such that the reflected rays graces on the reflected surface.
Well, I can get what you're trying to say, and it's basically correct. So the critical angle, which I'm going to
say that probably over the first term there should be some basis vector. If you look at that one, the second term you have basis vector, and like first term there should be top.
You're right. Thank you for catching that. So, essentially, what he's saying is, what we derived was that this is, by the product rule, going to be equal to the derivative of this, which is equal to this. Oh, wait, sorry. This times the basis vector plus the derivative in the basis vector times the original. So, yeah, okay. So that is very good. Thank you for catching me on that. Speed of light being constant in all reference frames, of course, comes from the 4 Maxwell equations. And why is it significant? A regular Euclidean point in space, what is the only thing that is invariant in R3, no matter what reference frame you're in? The only thing that's invariant is distance. Velocity can change. Acceleration can change. Position can change. But the only thing that doesn't change is distance, no matter if you rotate your reference frame or you translate your reference frame. So, this velocity of light has to stay constant in all reference frames, but this contradicts our normal sense of velocity in Newtonian mechanics. So, to change velocity, which now has to be invariant, to keep velocity the same, we now have to change distance and time, which were originally invariant. And so, this results in length contraction and time dilation, some certain Lorentz transform to account for the fact that the speed of light has to be the same. So that's the significance.
Where such huge value of pi is being applied?
Nowhere.
Nowhere.
Absolutely nowhere. How many digits of pi your computer can calculate, and not in terms of applicability, but it shows how powerful your computer is. So essentially, when we get a new record for pi, that's not because we want to apply it, but because it shows we've got a new record in computational power. Thank you.
Thank you. Okay.
So children, our contemporary Einstein is present in front of you. And give him a challenge.
If a twice differentiable function is symmetric about the line, say x equals a, then can we say that its second and third derivative would also be symmetric about that same line?
Oh, okay. So a twice differentiable function.
Or thrice differentiable.
Oh, 3 times. Okay, I see.
Like little brief about what are dimensions. Like from 4D onwards, like we know about the x, y, and z axis of 3D. So when it will be 4D, what is the extra axis that will come, and just a little briefing about dimensions and all.
Of course. So let's say I pick up this tissue box right over here. So then this tissue box looks like this, right? So we've got this tissue box looks like this. And of course, I'm the best artist in generations, so you can obviously tell this is a tissue box. So this is the length, this is the width, and this is the height. All we mean by 3 dimensions is 3 metrics that we use to specify the size of any object. So, using the length, width, and height, we can say that this object has some sort of size. And the reason we use them perpendicularly is very simple. It makes our volume and area calculations very easy. So if we have a sheet of paper, usually the thickness is negligible. So we talk about the 2 metrics that we measure it with. We measure it via the width and via the height. And so if we're in 4 dimensions, then we use 4 metrics to measure it. But of course, we haven't come across any objects that need that in the real world. And so since we don't need it in the real world, we can't imagine what it would look like on a sheet of paper or a smartboard. It's a very nice question. And actually, the reason I said, what if we're in the 27th dimension, which apparently seems a little bit confusing, this essentially just means we have an object that needs 27 perpendicular axes to measure. Of course, there's nothing like that in real life, and there probably never will be. But this allows us to generalize any vector, because the vectors that we have in our life usually have 2 components or maybe 3 components. But it turns out in general relativity, most vectors have 4 components because they have to account for time. And if we were doing general relativity in any other dimension, which seems to be useful for other applications like string theory, we could have even more than 4 dimensions, maybe even 12. So we just generalize any vector because it makes things easier for us to do in higher dimensions, which we often need to do when considering theories that utilize higher dimensions. Of course, we already can see 3D in real life, but when it comes to 4D, which is what general relativity often uses, we can't actually visualize that. So we simply have to generalize it. When it comes to, for example, string theory, which has 11 dimensions, or so I've heard, then we need to generalize that even more because that is beyond human imagination. And finally, when it comes to the axis that is beyond x, y, and z in 4th dimensions, doesn't have an official name, and any official name isn't important, but most people opt to call it W. So thank you for the question. It's very interesting.
The open interval 0, infinity to real number r.
Okay, got it. The f prime of AB is equal to f prime of A plus f prime of B by this rule. Essentially, f prime of x squared is equal to f prime of x. So, of course, if we plug in 1 to this formula, we get f prime of 1 equal to f prime of 1. Essentially, if f prime of 1 exists, which proves this equation true, because f prime of 1 is equal to f prime of 1, then if f prime of 1 exists, this equation is true, which, since this equation is valid for all real numbers, then that means that it exists in all real numbers. Wait, let me see. I got it. Fn plus 1 of 3 is equal to 1 minus 2n over 5 and equals 1, and we just keep going. So this gives us a value for every term.
Matter of privilege to get Professor Suborno Isaac Bari amongst us. So it's a historic moment. So give him a challenge.
A current I flows in, can I hold this? Current I flows in an infinitely long wire with a cross section in the form of this is choice 3. Yeah, it's 3. You take the second derivative, both sides go back to being positive. So that means f double prime of x does follow the criteria. And if it was 4 times differentiable, then any even derivative would follow the criteria. So it's a bit of a deep question. It takes a little bit of thought to figure out, but it should hold that any 3 times differentiable function, its second derivative should be symmetric around x equals a if it itself is symmetric across a. Thank you. Absolutely amazing. Yesterday's interaction session was great. The students responded very well to my speech, and especially their questions were very captivating. Some were about quantum mechanics, some about relativity, some about the creation of the universe, some about current and SI units. They were all very amazing questions, and I can't wait to be back here soon because of how captivating these questions were and how eager the students were to ask them.